to the continuation of the advanced toolchain usage discussion. I can't recall what the number of this session is. Was this SFO15-310, I believe? So this is part 6. This shares a slide deck with part 5. You can find the slides on SlideShare, I believe. All right, so I'm going to get us down to where we were at. So I'm going to apologize. I am a guest speaker on the next section. All right. So we left off discussing symbol versioning. Did anyone have any questions? We kind of had to abruptly cut it off. Did anyone have any questions on symbol versioning?
Oh, I have a question.
Sure.
What is the cost, performance-wise, of adding a new symbol version?
So in general, the cost is negligible. Actually, you won't notice any costs at execution time because you're resolving symbols through the PLT anyway. The dynamic linker is simply giving you direction to a different symbol when you use symbol versioning.
Yeah. Code size?
Code size, you're picking up a little bit more. No, I don't think you're picking up anything extra. You're just picking up an extra set of text for the version symbol.
And the function itself, implementing the new symbol.
Yes.
Yeah.
Yep. But as far as at execution time, there's no difference. There is an issue with this with static linking. That's what the libc non-shared is for. So you'll see the issue becomes a little bit more complex with static linking. But this slide set did not cover that. So I recommend you take a look at these resources. They're actually really good. They're useful, and I'm not saying that just because I wrote one of them. In particular, the examples near the bottom. All right, so the next section starts with a discussion of timers and timestamps. So this topic describes identifiers when certain events occur. So there's different accuracies and formats, and the history of these, I don't really have the historical knowledge of them, but as the demands upon the system for accurate timing have increased, new versions of timers and timestamping have come about that cost less and less. So ultimately, you don't want to have to pay a context switch and a syscall every time you ask the system for the time. So that's sort of the history of why you're going to see some changes. You'll see the old versions were syscalls, and the new versions are something much quicker. So these different timers and timestamps, they're provided by the operating system or by direct hardware access. So there's different APIs based on different standards. They have different precisions and different latencies. So for POSIX, we have time and ftime, which have second resolution. Get time of day, which has microsecond resolution, and clock get time, which has nanosecond. There's different reasons to use all of these. I believe in general these days, get time of day is the preferred, largely because of the fact that you don't pay the context switch. It's not invoked via syscall. That's actually invoked via the VDSO. So there are multiple functions to transfer between these human readable forms, as listed here. And these are usually implemented through precise timers such as get time of day. Get time of day is a really robust function. So this slide discusses the time frame in which this was introduced. Oh wow, I did not know that. Get time of day is now marked as obsolete, and the recommendation is used to get time. My assumption is that that is also implemented via the VDSO. Yeah, through either syscall or VDSO symbol. I'm not familiar with, very familiar with clock get time. I don't understand the issues between why get time of day was marked obsolete. Does anyone here know the reasoning? No? Where's Sadesh? Oh, he's not in here.
My completely uneducated guess is just because computers and CPUs are getting faster, so that time-stamping events at get time of day microsecond resolution is just not enough, because too many things are happening in 1 microsecond.
So we discussed, or as we saw in the previous slide, these are implemented often as syscalls or VDSO. And as I said before, you don't want to make a syscall to get a timer. So let's say you have a computer game on your phone, and you need to have a timing loop. So you need to have something happen with some frequency. And you don't want to have to pay the context switch. You don't want to make a syscall. Go into the kernel and get the answer back. That just sucks up valuable resources, valuable time. So what came about is the VDSO, which is the, I believe, Virtual Dynamic Shared Object. So this is something that the kernel exports that looks kind of like a shared object. That's not really a shared object because it doesn't have a file presence. It's just something that's available in memory for the dynamic linker to utilize at runtime. So this is a very convenient way for the kernel to communicate with user space. Basically, it's a spot where while the kernel's running off in this thread, it's updating the VDSO, and while user space is in this other thread, it's looking at what's in the VDSO. So it doesn't incur a syscall overhead.
Yeah, and in this sense, VDSO is just looks like a shared library. It has some variables. It has some code in it. So when your program utilizes VDSO, what usually happens is it jumps to a code section of VDSO, executes some instructions which fetch value of a variable and return it in a register.
Just a word of warning, if you try to treat the VDSO like a shared object, you will be sorely disappointed because it's not, it does what it needs to satisfy the requirements of the dynamic linker, but that's about it. Don't get crafty with it, you'll just get burned. So Adhemerval had listed some latencies to compare the different syscalls. Let's see, what are they? Yeah, I think you said clock get time is now the new recommendation, so let's look at that. Yeah, so if you look at the latencies there, this is pretty significant performance improvement on some of these. All right, so C11 provides a higher level API, the Chrono Headers. I don't know what Chrono Headers are. I haven't looked at C++11 yet. I guess the implication is that hardware might provide specialized instructions to access to higher resolution timers in user space. Is anyone familiar with C++11 and these APIs? Maybe Sadesh is. Put him on the spot when he walks in. Are you familiar with the C++11 high-level APIs for chrono headers and timers and timestamps? No? Okay. That's about all we had for this. Like I said, I apologize, I'm a guest speaker on this, so this is the first time I saw those slides as well. Any questions on timers and timestamps? No? Okay.
Who cares about these?
Which
applications?
In my experience, anyone who's doing timestamping, so for example, I've seen these in high-frequency trading when they want to record when certain transactions have taken place. But the simple act of recording a transaction can skew or can slow the program down significantly. So they need the most highly performing timestamping they can get. So they're often trying to use the VDSO implementations to get their timestamps. Game loops, I've seen this in video games. They want to know with some regularity event-based systems, so popping up events on a frequency or timer. All right, so I will pass this off to Maxim, and he can go into the next section of the presentation.
Okay, so the next part is about what compiler can and cannot know, what it can know in its optimizing an application, and what it cannot know, so that you have a reasonable expectation of what possibly a compiler can do. We are going to cover unit at a time compilation, then make a couple of notes about whole program compilation, talk about runtime effects of a system and the CPU and its memory subsystem and its core, touch on algorithmic optimizations and undocumented CPU features. So the main body of what the compiler cannot know is defined by what compiler can see when it's doing its work. In the traditional unit at a time compilation, the most interesting things to the compiler, some of the interesting things to the compiler are what functions does it see, what the variables does it see, and whether it can remove some of those. So generally speaking, unit at a time compilation, every unit will have some local functions and local variables, and it will also have some externally visible outside of the compilation unit entry points. If a file does not have any externally visible entry points, it can be as well just thrown out, because there is no way to get inside that code. What usually happens is that there is an external function which then calls local functions to do the real job. So, unreachable functions. If a function in the compilation unit is marked global, it is assumed by the compiler to be reachable. Even if global function in your compilation unit is not referenced anywhere in the program, compiler cannot possibly know that. And a function, that code, might very well be dead, but it will not be thrown out of your application and will consume RAM at runtime and negatively affect cache. Dynamic linker and static linker generally are not smart enough and will not care to scan your program and figure out whether some of the symbols are in fact unreachable. Similar reasoning applies to variables. To a lesser degree, because variables generally don't take too much space unless those are arrays. So a single int variable will not cause too much trouble, but a big array of a couple of megabytes, which is unused, can be a significant overhead in your program. And so think carefully whether you actually need any global variables. As a general programming guideline, I think it is advised, especially in the C++ world, to have access functions to all the variables and have as little global variables as one can in a program. Any comments on this statement? Agreements or disagreements?
I just read the same statement the other day, so.
Okay. Next point about unit at the time compilation is function binding. In the first part of the presentation, we talked about search paths and dynamic libraries and static libraries. And compiler, one of the important compiler optimizations is function inlining. So you would think that if there is a function A defined in your compilation unit, and then function B calls that function A, that the compiler should be able to inline function A into function B, right? Because there is the call and there is the body. But if it so happens that function A is a global function, then with, let's say, weak binding, then at the runtime, dynamic linker might issue a call to a different symbol, A, which is located in a different library. And compiler knows that dynamic linker can do that and is not able to inline function A into function B. Right? Because even though on paper it looks like compiler can know what will be called, in reality, just like with virtual functions in C++, things can change at runtime, and different functions can be called from the single, from different parts of the program. The last 2 points, big functions and big applications. Compiler is a memory and CPU hungry program. When it does its optimization, it can use several times more RAM to store the program and to optimize the program that it takes on disk to store it. So if you have a 10 megabyte executable that you're compiling, compiler can take up to 100 megabytes or a gigabyte of RAM to generate that executable. Therefore, compiler has to somehow deal with very big functions and very big applications. The normal way is that if compiler sees that the function, that its intermediate representation of a program is growing out of control and becoming too big and is about to overflow memory limits, it just cuts, it makes a cut of the program and says that I'm going to optimize this part, first part of the program and second part of the program separately. I'm not going to try and propagate information I know from the first part of the program into the second one and vice versa. So it encapsulates and compartmentalizes different functions and even different parts of the same function into different optimization units, if I may say so. Otherwise, it runs out of memory. So from a couple of years ago and up until now, whole program compilation is becoming increasingly popular. And the goal of whole program compilation is that to be able to give the compiler a view of the whole program so that it optimizes not function at a time or compilation unit at a time, but it optimizes your application as a whole. So that if you have function A in one file and function B in a second file, it can still do cross compilation unit optimizations. And this is done in as link time optimizations generally. So when you compile, first you compile individual files into intermediate representation, into bytecode of a compiler, and then at link time, the actual work of the compiler is done. When it has all the object files, before it links them together, it looks at them, it optimizes them, it does inlining, it throws away unreachable functions, unreachable code, unreachable variables, and has it has much more information about the program, as if all of your program was in a single file. Generally speaking, link time of whole program compilation is roughly the same as putting all of your application into a single file and giving it to a compiler. Development-wise, it would be a maintenance nightmare to have everything in a single file. But some projects did that as a workaround before LTO optimizations were mature enough to properly handle this use case. I want to say Perl, but I may be mistaken. I remember one of the big applications had a mode where it would include everything, all of the program into a single file and compile that one with a huge and long compiler invocation. So, whole program compilation allows compiler to more easily get rid of unreachable functions, unused variables, and prove that some of the variables are constant and are never changed after initialization, which gives nice benefits in where the variables can be placed and what other optimizations that can subsequently trigger. It cannot help with function binding issues because that still is out of scope of whole program compilation. That's at the scope of runtime and dynamic linking. And big functions and big applications are not affected because the compiler will run out of RAM even quicker in LTO because it sees a bigger program. Questions or comments so far? Who has used LTO to compile something? Who does not care about LTO at all and thinks that unit-at-a-time compilation is the only way forward in this world?
You're showing your biases here. Oh.
I think somebody was trying to compile glibc with LTO.
And the result?
I have no idea. It's a vague memory. If I find something, I'll let you know.
Relatively recently, right?
Yeah, relatively recent. I think around Cauldron or after that.
So it's very interesting to compile big projects like glibc or Linux kernel or some of the big browsers with LTO. And see what kind of benefits that bring. Quite often it brings both size reduction because unreachable functions can be removed, and some of the big, huge projects which have long legacies have quite a few unused functions that were added as entry points, and then they became unused, but no one noticed because no one audited that code. I believe at least Firefox and its libraries had, and possibly still has, some of that unused functions. I'm sure other big projects do similarly. Moving on to other part, next step of what the compiler cannot know is the runtime effects. So as we already touched on dynamic linker, compiler cannot know anything what is happening to an application after dynamic linker starts. In addition to function binding and symbol binding, compiler cannot know for sure what will be final layout and alignment of code and data. And most importantly, data arrays and how loops are aligned. So compiler tries to align code, especially hot loops, and frequently used data arrays to a reasonable degree, like 8 bytes, 16 bytes, 32 bytes, so that those fall in, play nice with microarchitecture, branch predictors, cache prefetchers, cache itself. But inevitably, some code and data layouts will be better than the others. If you, even at 32 bytes or 64 bytes, if you have a loop of about the same size as your cache line, you want that loop to be right at the beginning of your cache line. Because then you will not have to fetch two cache lines and your loop can execute without any delay on cache prefetching or cache fetching. Unfortunately, This is mostly controlled by the by the kernel that lays out the program in the memory. And aligning every single loop to a cache line size would be too costly. So be ready for some performance effects from data alignment. And quite often, the Toolchain team, the compiler team, gets regression reports that my benchmark or my application now runs 5% slower when I upgrade it to the new compiler. And several times the answer was that compiler did everything right, but because code generation changed slightly, the loop which was aligned at 32 bytes now, it is still aligned at 32 bytes. It was 32 byte aligned before, and it is similarly aligned now, but its layout is different on the cache line size. So your CPU gets a bit more overhead in cache fetching now that it used before, and compiler cannot do anything about that. This is just what we call compiler gets unlucky. Branch prediction, similar topic. Profiling helps with compiler getting minimizing branch mispredicts. But if your input is different from what compiler profile was run on, significantly different, you will get a lot of branch predictor misses. Also, the compiler cannot know the final balance between CPU and memory. As a rule, compiler assumes that all memory accesses are hitting level 1 cache. So when there are compiler models of your CPU in the compiler, when there is a memory reference, they assume a level 1 cache hit. And if that is not happening, you are always hitting a level 2 cache or level 3 cache. Whatever else compiler is doing, whatever else it is optimizing, it will not be effective because your bottleneck will be the memory, not the core itself. Second to last point is algorithmic optimizations. This is a fairly straightforward one. Compilers do not optimize algorithms. If you are implementing a substandard algorithm or your code is less than perfect, compiler will generate very nice instruction sequence for that code, but it will not try to warn or otherwise advise that you are using suboptimal algorithms. One exception to that rule is that compilers can sometimes transform simple recursion into loops, but that's about it. Other examples of compiler doing algorithmic optimizations?
Will it hoist variables outside of loops, even in stupid algorithms?
Will compiler hoist variables outside of loops? Yes, it will. It will not change it will change references to the variables because they will be still the same loops, but yeah, it will generate faster code with what it got. I guess one other kind of algorithmic optimization the compiler can do is that if it sees consecutive invocations of sin and cosine functions with the same argument, it will transform that into sin cos invocation, which computes both values with a single function.
Not that it will help much. Not that it will help much because the current sin cos implementation just calls sin and cos. It doesn't actually use anything.
It depends on the library. It depends on the library.
Yeah, so I'm telling you what the library does because So the assembly, I believe x86 had an assembly implementation of syncos. I don't think anyone else does. And that was removed about 2 years ago because it wasn't accurate. And it was replaced with the syncos calling syn and then cos.
You get a little bit of code size help, of code size improvement.
So that is a project in glibc that if someone's interested, they could take it up.
And finally, compiler cannot know what compiler engineers do not know. So undocumented CPU features, if you don't tell compiler engineers about what your CPU actually does or what it actually doesn't do, like it has bottlenecks, or it does not execute some of the instruction sequences in time it takes to execute every individual instruction sequence. Like if there is 3 adds in a row and then multiply, it will somehow be very costly to do, to execute that instruction sequence because of internal microarchitecture. Compiler will do nothing, right? So this is a call for all microarchitecture vendors and CPU vendors out there. Tell compiler engineers everything you can about your designs, about your cores, because then we can teach compiler how to work around and generate best possible code for your machines. A special note should be made about CPU bottlenecks. Very often optimization guides say what CPU architecture is and how many CPU units does it have for arithmetic, for FP, for memory, but it does not always mention the bottlenecks. Like branch predictor is often a bottleneck in this implementation because the buffer turned out to be too small, something like that. Tell us about bottlenecks. They're very important to model in the compiler. Questions or comments on what compiler cannot know?
Yeah.
So can the compiler optimize across inline assembly? So if you have C code, include inline assembly, more C code, can it optimize across all those?
So depending on the compiler, GCC can optimize C code around inline assembly. For GCC, inline assembly is just another statement. Nothing more, nothing less. It's a statement. And developer is responsible for accurately describing every single effect and side effect of that statement. So if compiler can see that there is inline assembly, but it doesn't have any side effects, I can throw it out easily. Or it can see that only registers are touched in that inline assembly. It can propagate alias information about pointers across that statement, no problem.
So what about where the inline assembly starts with a certain instruction, and the C code that's generated, the instructions that are generated from the C code prior introduce a hazardous set of sequences? Can the compiler know that I executed this, or I inserted this instruction here, the inline assembly starts with this instruction, that pair is a hazard?
For GC, it does not know that. I believe LLVM looks into inline assembly and parses it. So whether it then tries to optimize based on that behavior, I do not know, but at least it looks. GC has a view that inline assembly should not be looked into and tried to be parsed. And the hazards you are referring to here are performance hazards. So they can reduce performance of your application, but they should not change correctness of the program. it can be tricky on some of the explicit pipeline chips, like some of the DSP chips, but that just means that inline assembly should be used extremely carefully on the chips with explicit pipelines, which ARM and AR64 are not. Any other questions about optimizations, compiler optimizations? What can it and cannot do? Okay, moving on. The last part of the presentation of the session today is about out of order versus in the order execution cores. And this is not as much us talking to us as a discussion of what are good use cases for out of order cores and what are good use cases for in order cores when one should be used versus another, and how they can be nicely combined into big little configurations. So main difference between out-of-order cores and in-order cores is how smart CPU thinks it is. Not necessarily how it actually is, but how smart it thinks it is. Out-of-order cores, first, in-order cores see instruction stream and follow that instruction stream to the letter. They do not try to shuffle instructions around. They do not try to execute part of the instruction streams before the other parts. They don't try to find the dependencies and work around those dependencies. Out-of-order cores, on the other hand, look at the instruction stream as a program that they can potentially optimize and that they can execute in a different order from what the compiler is given to maximize performance. In the ideal world, if compilers were infinitely smart and infinitely complicated, there would be little need for out-of-order cores. Because compiler will be able to figure out every single alias, what every single pointer is actually pointing to at what time of the program. In reality, programs are very nonlinear. They can take different branches, and pointers can point at very different locations in the memory. So if out-of-order core has a big enough buffer of, let's say, 16, 32, 64 instructions, it can look at those instructions and see which ones it can execute right now and try and fill as many execution units as the core has. Comparing this to in-order cores, in-order core will have its execution units idle while there is an instruction, even if some of the instructions can be filled to those execution units right now. Cost-wise, and cost meaning silicon, the out-of-order logic tends to take quite a bit of silicon on the core. So if you are, and it also needs power and energy for its work. So if you are, and the main benefit of out-of-order core is faster execution speed. So, but if you are not pressed for time, if your CPU is idling anyway, there is not so much need for the additional performance. So as we can see in many big little configurations, little cores are used specifically for the low performance tasks, and while they get the job done, they do not drain the battery, and there is no noticeable difference to the end user. Even with the fact that out-of-order cores try to be smart, they still benefit from various compiler optimizations like instruction scheduling. Because instruction scheduling can try and form the instruction stream in such a way that it will be natural and easy for out-of-order core to fill all of its execution units. Like compiler will try to execute several arithmetic instructions together with a couple of memory instructions, and it knows that out-of-order core has about 3 arithmetic units and a couple of memory units, and those will fill up nicely. As it is currently the case, I believe, and someone can correct me, all little cores are in order, and all big cores in big little configurations are out of order. So what the compiler should do and how should it optimize when compiling for a big little configuration? Should it optimize for the little core, or should it optimize for the big core? The answer is somewhere in the middle. When optimizing for speed, optimizations which are mostly concerned with speed, like instruction scheduling, they will tend to optimize for the in-order core, because that's where scheduling benefits most. On the other hand, other optimizations, which are mostly concerned with code size, they may optimize for the out-of-order core. So there are special -m CPU values, which are in the form of -m CPU equals big.little to specify a combined profile to the compiler for optimizations for the big little cores. Also, as a general rule, A-profile cores, big cores tend to be out of order, and little cores to be in order. In the R-profile cores, which is a real-time profile, most cores are in order. There are a couple of out of order, but generally real-time systems prefer in-order cores which have as little variance in performance as possible. M-profile, like R-profile, mostly in-order cores, because those are small microcontrollers which are not very much dependent on performance. And this is the end of the presentation. Questions on any part of the presentation, either about big, little, out of order, in order, what compiler cannot know, or can know, and optimize.
So the
little cores will suffer the most from suboptimal instruction ordering, right?
Yeah.
Okay.
Because they cannot do anything about it.
Right. Any other questions? All right. Well, thank you, Maxim. Thanks for coming to this sequence of presentations. We'll probably continue on with the same series next Connect, so please look for us then. And we'll add these slides to SlideShare. So thanks for coming. Bye-bye.